Well, hi, in this riveting episode of Tim Time Projects, we're going to mess with a older oscilloscope there and just see if it still works. I haven't used it in quite a while, and I just want to run it through some tests and see if I remember how to use it. Alright, got it plugged in. Let's turn it on. If you look, you'll notice there's another scope back here. I don't know if the camera's letting you see it. It's right behind this one. It's same thing. It's a digital oscilloscope though, so that one's more like a computer that will display something on the screen for you, whereas this one is kind of a direct feed, for lack of better explanation. But so let's see if we remember how to turn this thing on. There's a power button, so I have it plugged in. Let's see. Oh, there it is. It was turned on. I expected the power button to light up, but I guess not. So let's turn that down a little bit. We don't need all that intensity. I'm always afraid I'm going to burn through the screen with that. So all this does is your voltage divider. See these little squares here? It tells you what each square will equal. So we're not going to worry about all the different options or anything, but we can turn it so, just for simplicity, that each square right here, the 1, it says times 1, each square equals 1 volt. So if my little line deflects up or down one way or the other, 1 square would be 1 volt, 2 squares 2 volt. So you could go all the way up on this scope to basically each square being 10 volts. So you could go 10, 20, 30, 40, and you can even kind of move your move the positioning down on that, so you could go even more up or down. And you'll notice there's a 0 line here. So if I put this on ground, that's just my connection. It means nothing's connected to that right now. The 0 line would be truly 0, no volts. So if I we'll just grab something. If I put something in that's 5 volts positive, it'll go that way. 5 volts negative will go that way. So let's take it back to 1. We'll leave it right at the 1. And I'll go find a battery or power supply or something, and we'll test that, and you'll see. And as far as the probe goes, there's 1 times probe, 10 times probes. We're just going to be working with DC and maybe a little bit of AC. I'm not even going to bother with all that probe stuff. I'm just going to use a set of positive and negative leads. We'll worry about probes later when we use it for AC or RF and audio frequency signals. The probes help keep it silent. So let me get a battery of some type that we can use, or a power supply, and we'll go from there. Alright, well, while we're at it, we'll talk about making the trace go that way too, and that's going to be this one. And if you look at it, let's see if I can lighten it up a little bit here. You can look at how slow I'm making the trace go. If I want to measure something, that, at least for DC, that's not going to be real helpful. So what we're going to do is we're going to make it just fast enough, and I don't want to have a seizure by having it at that frequency. We'll speed it up enough that it's moving. I don't know how that looks to you. See, that's affecting. To me, it's a solid line, but it's flashing. Now in the video, because the scan rate of the video, it's probably trying to almost 0 beat it. So I'm going to move it up a little bit till it looks just like a line in my monitor. That's what it looks like now. To me, it looks like a line right about there. This is more for when you're measuring AC waves, how much of the wave you can fit into the screen. And I'll show you that briefly as well, but for now we're just going to look at, we want to use this just like a voltmeter. So I'm going to zoom you out a little bit, and I always go the wrong way. Okay, so we're out as far as we can go. I'll see if I can move this into the screen a little bit more here. Just a Radio Shack voltmeter. So we're going to turn this on AC and DC. Excuse me. we're going to use DC. And that just basically means you have a direct connection between your leads and whatever you're testing. This, we know the output's a Radio Shack power supply, should be around 12, 13 volts. So, let me not touch these together here. So, remember I said we're going to use the ×1 multiplier, so each one of these squares, and hopefully maybe I'll zoom in a little more so you can see the squares I'm talking about. There you go. Okay, so this is 13. If I do it ×1, I'm going to need 13 of these squares, so we'll be way out of control. So I'm going to make it so each one of these squares is ×5. So it'll be 5, 10. So it should be probably not quite to the bottom of this square here, or that's positive going up 5, 10, not quite to the bottom of that square, the top of that square. So without any further ado and me babbling, let's put our 12 or 13 volts on here and see what we get. There, I've just connected the ground. And now when I put the positive on, there it goes. I'll quit touching them together. So it looks like it's almost 15 volts. 5, 10, 15. This thing at the top here, that's kind of what we're interested in with power supplies. But we're not going to talk about that right now. But that's kind of probably the ripple that you'll get, or you can hear sometimes when you get a DC power supply. I can grab a better power supply and we'll put it on there. We might not see that as much, but we'll look at a different way to measure that. But anyhow, that's it. So you see that when we tested it that way, it went up nearly 15, and I guess that's about 13.8 or something on a power supply until you put a little bit of a load on it. So let's take this back off and look. And I'm actually started a little bit high too on that. If I zero this down, oops, wrong. I move that position so it's directly in the zero there, and try it again. Yeah, it's just short of 15, so it's about 14 volts. And again, it's got that ripple in it, so that's making it. But when I turn it the other way, if I want to reverse polarity it and say touch black to red, red to black, now it goes the other way. So that's what I mean. The true line I made, this going across zero, everything positive voltage would be that, everything negative voltage would be that. So there you have it. Now we've just used our oscilloscope and we can use it as a voltmeter. You're going to find, remember I was saying about making the trace speed up so that you can live with it. That wouldn't be that easy to measure make your measurements if it was like that. So when you're measuring for DC, just make it so that you can see a line. You can see I can go up into the megahertz zone, and it has no effect on it for DC. So we'll go back kind of where we had it, which was right about there. So now what happens if I turn this back to ground, and that means it's kind of like there's nothing connected now to the leads, but you can still see. I'll zoom you out a little bit, the other out when I'm still connected here. Turn it on. So how about if I put it on AC? On AC you'll notice that it's not going up anymore, but it's still starting to show me that ripple. And that means because it's basically connected through a capacitance, which is blocking the direct connect, which would be the DC, but letting the AC go through. So let's see what kind of noise I have with this power supply. And this is an older, cheaper power supply. It's probably been rebuilt 1,000 times, but it's probably about 40 years old. So what does that say for the capacitors? So we want to get a closer look at this wave that's here. So I'm going to put it on the times. We'll go 0.5, and we want to make sure that we can get this whole wave in here. Look at that. That's just the AC component that is still inside the power supply that the filtering unit hasn't taken out. We're not looking at any of the DC stuff. This is just the AC that's riding on top of the DC. If I turn this to DC, it'll shoot off the scale because I'm at 0.5 volt, so boo, it's gone. but I can bring that back down. Again, this is just your times, your multiplier. So we're back at 5, and you can see that we're riding on there. I'm going to switch the polarity around just for simplicity's sake, so I don't keep making a mistake and saying positive when it's negative. So okay, here we go. So here you can see that's the AC component. That's the noise that you would generally get in your radio. If you put some capacitors in parallel with that, or at least a capacitor to ground that would pass some of that, or even a choke in series, a lot of that will go away. So let me grab a more high quality power supply. What did we say? Let's go down, before we do that, let's go back just to AC. We just want to measure that. That's at 0.5 volt, and it's taking up nearly 3/4 of these. So well, let's see, let's put it at 1 volt, and we'll just kind of get it in here. So there's almost 3/4 of a volt AC riding on top of the DC. So let's see if maybe a better quality power supply would not have that same, or maybe not quite as much. So I'll leave it set like this, go get a different power supply, and we'll plug it right back in. Okay, so now I have my trip light power supply. Try to see so you can get a look at it. And this is what, a 15 amp. I think the other one, that was a 2 amp. This is a 15 amp. And I'm going to try and plug this right into this and see what we get. Alright, so there's the positive, and there's the negative. I'll turn it to ground. As you can see, there is almost nothing whatsoever when I turn that back to AC. Let's turn it to DC and see what we get. Of course, it's off the screen. So let me turn it to, remember we went 5 volts, and let's position this again right in the center. And when we turn that on to DC, see it goes up to about almost 14 volts, and there's not that rowdy thing, that waveform that we saw. And if I look at it on AC again, there's almost nothing. Let's zoom that in as far as we can. Look at that. Each one of these is 0.1 volt, and it doesn't even hardly move. So that shows you this is a much better power supply than that, at least as far as noise is concerned. So one less power supply to look at. Why don't we try a switcher power supply and see if the same holds true for that. And here is my switcher power supply, and again, these are all with no load on them, so things could change. Here's that switcher power supply that's in another video that I put together with this box on it and everything. Let me pause you while I plug this in. Okay, so here goes the switcher. It's sitting upside down just because that's easier for me. So we'll put this on, that onto the negative, this onto the positive. Now you can see it got a little, let's just convert. You can see it got a little bit noisier, but that noise, you're going to find out, is way higher in frequency than the noise from the original power supply. So what do we know? The original power supply had a lot of noise that you're going to hear at 60 hertz probably, or somewhere right around 60, maybe a multiple of 60. The trip light, it was not a switcher power supply. It had almost no noise. The switcher has very little noise, but as you can see, it just got blurry. We couldn't really make out what it is. We're going to look that up in a little bit, but let's see. Let's just look. Oop, let's turn it back to 5 volts again. 5 volts. You can see it just under, it's about 13, well, it says 13.7. That's probably right about where that should be. So let's go back and see if we can even see where that noise is. We're going to turn this way down again. Okay. There's the noise. Let's see. Oh, I'm going the wrong way. There's that noise. Now that's a ringing kind of noise. And probably if you put a load on this, that may pretty much go away. I don't have a radio down here to put a load on it right now, but we can figure out the frequency of that. And that's what this is about. That'll tell me how many seconds per division each one of these is. So we could kind of, it's going to be a little bit hard to find. So each one of these, if this was to stretch out, we'll see if we can stretch it, and then we can send the positioning that way too. But that looks like probably one cycle in between that one division. And we are using, I'm trying not to put my face in front of the camera, we're using, let's see, where are we? That's of course right on the other side. 2 microseconds per division. So using math, we could flip that around to get that frequency, but that's not really what this is all about right now. But the time in microseconds is the reciprocal of the frequency. So we're not worried about that, but we're just saying that's really high up there. So that wouldn't be something you would typically hear. That's up in the megahertz range, I would assume. So yeah, it is definitely a noise, and it could cause some issues, but it's not something that you're going to hear like a hum. Okay, enough said about that. Alright, so this scope is a 2-channel scope, and all that mainly means is that you can monitor 2 signals at one time. Now, scopes, they trigger on the input signal, and what that means is when a signal comes into it, that's what makes the scope start to do its thing. Again, not that important for DC, but for AC, you might want to see that. You might be, say, working on a computer and you want to know a clock signal. So in order to get that to figure it out, you want to tell it, hey, when that clock signal turns on, trigger, so I can count it and see what the frequency is. When you have a 2-channel, it's only going to trigger on 1 channel, and you can usually pick this out over here with one of these knobs, and it tells you, hey, which one do you want to trigger on? Again, that's just more stuff you can do with the scope. The scope's really good because it's a voltmeter, but it can actually stretch out. With a voltmeter, you're only seeing here and now, and they can't be as fast as this. For instance, a voltmeter may never see the ripple that you get in power supplies, you know, from bad regulation or bad filtering, but this will see it because it's kind of looking at it in a time window. So that's one of the advantages. But you can use these. These are good for oscilloscopes. Are great for automotive things. If you're wanting to watch spark or triggering of certain things, you know, you wouldn't put them on the spark plug, obviously, but that's how some of the old ones used to go. They would look at the ignition coil. Great for computers, great for radio work, because it's actually giving you more than just a number. You can see certain aspects of the voltage or the wave, and of course, like I said, you can use it to calculate frequency. All right, well, I hope that was a little bit helpful for you, and it kind of helped me make sure that this is still working, and renewed my memory on using it a little bit, and also helped do a little bit of research on some power supplies and which one I probably shouldn't be using for radio stuff. The old Archer, or maybe it needs revamped. So anyhow, thanks for watching. Take care.